Hi, my name is Stella, and this is our final presentation for the RAFI group. So our team consists of our external mentor, Aaron, our internal mentor, Todd, TA, Rita, and Yuxi and Hao and Hantao. So a little bit more about RAFI. So RAFI stands for the Rural Advancement Foundation International, and they're a nonprofit organization that aims to advocate for farmers in rural areas. There are three main initiatives that they have. First is to challenge corporate power. Second is they have agricultural conservation and market access manager. And last is they have a farmers of color network. So specifically, our group is working with RAFI under the challenging corporate power initiatives. So a little more about what essentially we're doing. RAFI is dealing with a lot of poultry farmers in the rural areas. And so think about, farmers selling chickens, ducks, things like that. And so one big issue with regard to these farmers is they actually don't have access to a lot of corporations that they can sell to, even though the market can seem competitive from a zoomed out perspective, especially in more rural areas. A lot of the larger corporations, like one or two of them, control a large area. So farmers can only sell their poultry to these larger corporations in a not very competitive price. And this phenomenon is called oligopsony or monopsony. So what RAFI aims to do is they wanted to increase regulation for these larger corporations, and they hope to help the small farmers in this way. And in order to do that, we need to get a clear understanding of how exactly these markets are concentrated. And previously, there is this Microsoft model in which they were using aerial photography to identify poultry barns. And so our goal this quarter is to improve upon this accuracy, the accuracy of this model in identifying poultry farms. And there are two main things we did. From a rule-based filtering side, we filtered out a lot of the false positive predictions within the previous model by adding new GeoJSON files. And in addition to that, we also made a data labeling interface. So now we have this interactive interface where RAFI staff can use very easily to label false positive and true positive for any sort of future augmentation of data. And we also created an interface for data validation. So we'll be able to understand, what's the accuracy rate, what is the recall and precision rate for our model. So now this is just a quick overview of, what the predictions look like. And we were filtering out a lot of these predictions. We're doing validation on a small part of, the predictions. So now Hantao is going to talk a little bit more about the first part, which is rule-based filtering.
Hi, everybody. So first of all, as Stella has mentioned, our departing point is a computer vision model, which was designed and implemented in 2021 by Microsoft. And the main goal of this model is to understand the spatial joint distribution of poultry barns and integrators in order to verify whether conditions for oligopsony exist. And one could ask, why using a spatial model for this? Well, poultry is a commodity that differs from others in the sense that it cannot be transported very far away in trucks. And this is a potential source of market power. In the slide, you can see a screenshot of an area of Arkansas with isochrome zones or buffers, which are colored depending on the number of integrators there. As you can see, some areas are marked in red, and this means that these areas have only one integrator. So potentially all the market in that area is just for them. There is no data set that lists all poultry farms, so finding them is exactly what Microsoft's model is trying to do. As you can see now in the slide, a lot of farms are located near integrators. So those are susceptible to integrators' discriminatory practices, like imposing low prices, for example. The problem with Microsoft's model is that it includes a substantial number of false positives. So the aim of our filters is to remove them. And this way we can increase the prediction's accuracy. Let us show you an example to be more specific. Yeah. So this screenshot was taken from Hastings, Nebraska. And as you can see, some human infrastructures like roads or even some buildings are labeled as barns, even though those are obviously not barns. Hantao will show you also later some other specific examples. The model was trained using images from the Delmarva Peninsula, which is located in Delaware and Maryland, and its predictions are very accurate for the southeastern US, but not for other states. So in few words, our main concern here is that the model generalizes poorly outside of its training distribution. Obvious reasons for this would be landscape differences between different regions in the US, for example. In the case of Nebraska, it flags almost anything that appears to be rectangular as a poultry barn. So because the accuracy of this state is particularly low, we consider it that it could be a great candidate for checking the model's performance and to fine-tune it by applying our filters. So hopefully you remember this image Stella showed before with the raw predictions of the model for Nebraska. So each prediction barn is marked in blue, and there are about 6,000 predictions. However, as I said, a lot of them are false positives. So we apply our filters, and now we obtain a new prediction set, as you can see in the new image. The number of predictions falls to a bit less than 4,000. So this means that we are able to filter out more than 1/3 of the initial predictions. What kind of filter did we use? Well, first, we manually check the predictions. And second, based on this, we decided to apply filters for coastlines, airports, parks, mountains, roads, downtowns, and water areas. Applying these filters mainly consists of obtaining GeoJSON files with the location of these elements, of course, and adding them to the output of Microsoft model as a new layer. Importantly, filter out predictions are marked, and this allows us to later verify that we are not excluding true positives. In general, this process has proved to be effective, but unfortunately, even after the filters, a lot of false positives remain. And this is why the validation part of our work is so important. Hantao and Yuxi will explain it to you.
Hi, my name is Hantao. I will walk through the first part of our data labeling interface. As Anho previously mentioned, our predictions still have many false positives, particularly in certain states like Nebraska. The image below shows an example of false positive we found in Nebraska, where the model incorrectly identified house, train, highlight of the forest, and also water body as barn. To address this issue, we propose developing a data labeling interface. While introducing human effort to clean up the false positive may seem time-consuming, it will provide valuable data for future model fine-tuning, significantly improving the model performance. We have developed a data annotation tool, aka Tinder for bar. These two allow users to manually verify if the selected image contains barn. Additionally, at the request of the RAFI team, who has less technical background, we integrated our tool into Google Colab to enhance accessibility. Next, we will demonstrate our tool to provide more detail. So the image you see right now is the interface displaying a zoom-in map with specific prediction in the model. What users need to do is to click the button right behind to choose whether the image contains real ball. So if the image contains real ball, the user should click true positive, otherwise it is false positive. However, this section only covers the prediction made by model. In the next part, Yuxi will discuss our efforts to address the scenario where a bar exists, but the model fails to detect it. Thanks.
Hi everyone, my name is Yuxi, and following Hantao's introduction of our data labeling interface, which simplifies the process of flagging false positives, I'll now focus on the second part of our data labeling, the validation sets across multiple landscapes, which includes a comprehensive assessment of both false positives and false negatives. So this is a key tool that enables us to evaluate our current model and also improve our future iterations. And this screenshot shows how we do it. Firstly, how do we select the validation sets? We pick a random central point and generate a bounding box around it to select 50 barns. Then we can click the buttons to label false positives and false negatives. For example, in the top screenshots, the rows are misidentified as barns and they're marked as false positives. In the bottom screenshot, the barns that were not detected are marked as false negatives. So each click will store the information of the identification. finally, after we do the review for a random B-box, we can plot the confusion matrix to evaluate the model's accuracy. So here is the confusion matrix for North Carolina and Nebraska. As you can see, our model performs quite well in North Carolina. The precision is 0.86, the recall is 0.81, but it underperforms in Nebraska, where there are still many false positives. The precision is 0.1 and the recall is 0.56. So as we show here, the validation sets can help evaluate our current model and enables us to check if we are excluding too much or if we still have too many false positives. Also, these validation sets will be important for a future fine-tuned version of the model, as we now know the locations of all real positives. And this makes us to keep improving our model and making it more accurate and reliable across different landscapes. So these are what we did this quarter. Our main tasks include the rule-based filtering and the data labeling interface. So by reducing more false positives and allowing labeling of false positives, true positives, and false negatives, we improved our computer vision model that identified the partial bias and enabled the evaluation of this model. So in the future, we will retrain the model. Actually, we have already made some preparations for it, like making it possible to run the training script. And by continually improving the model, we can create a more accurate dashboard to display livestock concentrations. And this will help our client RAFI to estimate the number of farmers impacted by oligopsony and make the impact on small farmers clear to regulators, and then advocate for meaningful policy change in the livestock industry. Thank you.